Hello guys, welcome back to our channel Career at Market Value. So the topic of today's discussion will be some key definitions and terminologies regarding the heteroscedastic models. Okay. So the next slide talks about the value at risk normal distribution. Basically, we are always concerned about the left tail probability when we are estimating VAR or value at risk, which is shown in this slide. You can see the left tail probability is measured, which is 1 day 1% VAR is 0.05825. So yeah. Now comes the important point of data stationarity. Guys, it's very much important when you are doing modeling exercise on any of the asset classes which gives daily prices. Your data series should be stationary. So why your data set should be stationary? Because non-stationary data may lead to spurious regressions. The t ratio on slope coefficient would be expected near to 0, r square would be expected to be very low, or this could happen that your r square is pretty high, though your independent and dependent variable are totally unrelated. Still you have a high r square. Then the t ratios will not follow a t distribution, and the f statistic will obviously not follow an f distribution, and so on. So that's all about your non-stationary data, the problems that you face if you have a non-stationary data. Now we should come to the heteroscedasticity. Now what is heteroscedasticity? Heteroscedasticity refers to the circumstance in which the variability of a variable is unequal across the range of values of a second variable that predicts it. Basically, it talks about inconsistent variance, where variance increases over time. It's not similar throughout. But how do you come by a non-stationary variance data? So a simple generalized models won't work in a non-stationary data series. So you have to come by more robust and more modified. So this is basically the output from eViews. I will discuss in detail how to do the testing for data stationarity in eViews probably in our next video. So basically this table talks about data stationarity. You just have to look in the Durbin-Watson test statistic, which is 2. So when your Durbin-Watson test statistic is nearer to 2 or 2, so that signifies your data as stationary, and your probability is also significant. So we can reject null hypothesis that your data has a unit root, so your data is stationary. Now the next table talks about testing for arch effects or the heteroscedastic test, whether your data have inconsistent variance throughout. So the test for that is heteroscedasticity test. This is also performed in eViews. So here also we just need to look about the probability. You can see the probability of f, probability of chi-square, and both of them are significant. So we can reject null hypothesis, which is basically your data is homoscedastic. That is the null hypothesis. So we can reject the null hypothesis and agree that our data has heteroscedastic effects. That is basically talked about in this table. So the next table talks about the EWMA model, exponentially weighted moving average, which we have done in our previous video. Basically the risk matrix model, the variance that we have calculated, you can see the formula, lambda multiplied by long run variance plus of t minus 1 data point plus 1 minus lambda multiplied by return square of the t minus 1 data point. So basically risk matrix allocates a weight of 0.94 for the long run variance, and the rest of the weight, which is 0.06, is allocated to the return square of n minus 1 data point, which I have already explained in my previous video. So the EWMA model as applied by JP Morgan risk matrix is also in a way a kind of GARCH model or a heteroscedastic model. So we'll come to this in great detail when we'll be building our model in eViews. So this is we'll get the same kind of table. Now if I break down the term GARCH, so let me put this in a new slide. So GARCH, if I break the term, it's simply generalized auto regressive conditional heteroscedastic. My spelling for heteroscedastic could be wrong. Anyways, so GARCH is basically this thing. So generalized, it's obviously generalized, a simple model, and auto regressive. Auto regressive, which is AR, it's basically you are regressing or estimating your forecasted values based on the previous values or the historical thing or the previous set of values, as we have seen in the JP Morgan risk matrix formula estimation as well. I am regressing the dependent variable on myself only. So regressing a certain variable on itself is called auto regressive. Now conditional heteroscedastic. Heteroscedastic I have already talked about. We use the model for unequal variances, that is heteroscedastic, and conditional we will propose some conditions. Say for example we give this as GARCH 11. So this is the condition that I have given for the GARCH model. So that's about conditional. Now what is this 11? So GARCH 11 or ARCH 11 or ERMA 11, whatever you can write. So it simply says the first one over here is the AR term or the auto regressive term. So this is basically how much I am going to regress myself, whether through my previous set of data, or if I take this as 2, so there is a lag of 2. So the data point that I find 2 data points above, so I will regress myself with that, and so on and so. That is the AR term. And the next one is for moving average. Moving average is basically your errors. I mean, when you regress yourself, you obviously get an estimation equation and your original set of data. So the difference between them is obviously the errors. I mean, your estimation obviously won't be perfectly equal with the original set of data. So the difference between these two is the errors. So when you regress errors with itself, that is the next set of 1. So if I make this 1, it is regressing the errors with its previous data point that occurs one notch above errors. If I make this 2, then the error now is estimating itself with the error data point that have occurred 2 notches above. Now why do I keep on talking about errors? Why do we need it? Because you might be aware of a normal regression formula. You have a constant term, then you add it with some, say, x variable, and multiply that with another estimation number, say 0.256 whatever, then your next variable, and you multiply that with the next set of numbers, say. So that's how a normal, let me make it z. So that's how a normal regression equation looks like. But we are missing one key term over here, since your estimation equation won't predict exactly what your actual data set contains, or the number that your actual data set has. So there will obviously be a difference between the estimation equation. If I punch in the x and z values over here, the number that I will get won't be exactly equal to the actual data point. So there will obviously be a difference between the two. So the difference we represent by E, or the error. So that's why whenever you estimate equation for any model building exercise, say for GARCH class of models, or wherever you are running in regression equation, there should always be an error term. So you have to account for that. So since through our model we will be estimating the coefficients and the x and y variables, x and z variables, we also have to take into account the estimation for error. What should be the estimated error? That is taken care of by this second one, or the moving average term, which is incorporated in this GARCH class of models. So when it is GARCH 1.1, we are integrating our autoregressive models, that is this set of series, with its previous occurrence or one notch above occurrence of the figure. When you are estimating the error, we are basically talking about the next set of one that will be estimating the error when it is comparing itself with one notch above the error it has generated. So that's how the thing goes, and that's how thing works. So I guess guys, now the generalized autoregressive conditional heteroscedastic models, or the heteroscedastic models, is clear with you guys. So that's all from today's video then guys. So in our next video, I'll obviously try to build a model through eViews in the GARCH category, probably GARCH 1.1 models. I would like to show you guys how to calculate that. So before that, you guys probably should install eViews, the full version or the portable version. Any of those will do. So make sure you install them so that we are on the same page when you see my next video, where I'll be discussing the model building exercise with GARCH class of models. So that's all from my side guys, and make sure to share, subscribe and like this video if you have liked it, and do comment down below